Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now going to answer question number 6 from the May-June 2023 International A-Level Cambridge Paper 4 Variant 1 from the 9709 syllabus. And this question here is about these two particles P and Q, which have masses of 0.2 kilograms and 0.1 kilogram respectively. They are attached to the ends of a light inextensible string. The string passes over a fixed smooth pulley at B, which is attached to two inclined planes. Particle P lies on a smooth plane AB, which is inclined to 60 degrees to the horizontal. Particle Q lies on a plane BC, which is inclined at an angle of theta degrees to the horizontal. The string is taut, and the particles can move on lines of greatest slope of the two planes. Okay, so let's just pick out some of these things so you understand what they mean. A lot of students have problems with some of these words or some of these descriptions. So first of all, light, inextensible string. So the light part means there's no weight to the string, which means that, the weight of the string, if it's ignored, then the tension in the string in each section will be the same. So for example, over here, if it was not light, then the top of it would be also carrying the weight of what's underneath it. Okay? So it would be like the tension won't be the same all the way through. It will be varied if it wasn't light. Inextensible means the string cannot stretch. It's not elastic. So therefore, every particle that's attached to the string will have the same magnitude of acceleration and velocity, okay, as it's moving. Okay, so they're moving at the same rate because they're attached by an inextensible string, and that's, when it's taut, that will be the case. When it's taut means when it is tight, it's not loose. The string passes over a fixed smooth pulley, so there's no friction in the pulley, which means the tension on either side of the pulley will be the same. Okay, so fixed smooth pulley, fixed means it's fixed in place, smooth means there's no tension in the pulley, which means the tension on either side of it will be equal, okay, on the string, which is attached to two inclined planes. Particle P is on the smooth plane, meaning no friction. AB, which is inclined at 60 degrees to the horizontal. Particle Q lies on a plane BC, which is inclined at angle of theta to the horizontal. The string is taut, means there is tension in the string, okay, it's not loose, and the particles can move on lines of greatest slope of the two planes. So what is this lines of greatest slope of the two planes? What that means is basically how you can understand it. Imagine you were looking at this plane from this angle here. So you're looking at this plane from this angle here. What would you see? You'd see, like, just say you'd see a ramp going up, okay, and that would be 60 degrees, and you see a ramp going up. When it means the string is taut and the particles can move on lines of greater slope, means supposing the particle P is here, it's going to move straight up. Okay, the pulley's over here, it will move straight up. It won't be moving at an angle. It won't be moving from here across to there or there across to there. It will be moving up the line of greater slope, meaning directly up to the pulley. That's what that means. Now, none of those things actually in this question affect anything in terms of what we need to do. All right, these are modeling assumptions which they're telling us about, which we have to assume for us to be able to carry out these calculations. Now, in Edexcel questions, they sometimes do ask, how did you use the fact that the string was light, or the string was inextensible, okay, or the pulley was smooth? How did you use that in your calculations? I've not really seen that question asked in Cambridge. It's possible they could ask it one day. Don't know. But in Edexcel, I've seen them asked. So, for example, if they say, how did you use the fact that the string was inextensible? You say, we assume that both particles were, they had the same acceleration, for example, if they were moving. Or if the string was light, we assume that the tension throughout each section of the string was the same. Or the pulley was smooth, the tension on either side of the pulley and the string is the same, and so on. Okay, so those are some of the things that you might be asked about, which you should understand. Right, so now, in Edexcel, really they ask it. In Cambridge they don't, but you should understand that anyway. Then it says two particles P and Q of masses 0.2 kilograms. Okay, so I've got the diagram down here, and I want to answer the question that says, it is given that theta equals 60. So now we're told that theta is equal to 60. So this is 60 degrees here. So I'll just put 60 degrees here. okay, and the plane BC is rough. So now this plane is rough, so that means there's friction on this plane. This side was smooth, this side is rough. And the coefficient of friction between Q and the plane BC is 0.7. So the coefficient of friction is equal to 0.7. The particles are released from rest. Determine whether the particles move. All right, so there's two ways I can tackle this. I can tackle this by considering P and Q separately, and I can consider this as one whole system where I don't have to think about the tension inside the strings. So let's start by considering P and Q separately, okay? So what I'm going to do is I'm going to draw the forces acting on P. Now the forces acting on P are basically the weight, which is vertically down. I'll draw it all the way down here just to make it clear, which is going to be 0.2 G newtons. 0.2 G newtons. That's going to be basically 2 newtons, because G we're going to take as 10, because that's what they do in Cambridge. And the weight of Q is going to be 0.1 G newtons, which would be 1 newton. Okay. Now, we also have the tension in the string. Okay, in this case, it will be acting up. In this case, it's also acting up on Q. So there's a tension in the string. The tension is the same all the way through. So the tension here and the tension there will be the same. Okay. For P, I don't really have to think about the reaction force because we have no friction on this one. But for Q, I'm going to think about the reaction force. So I'm going to put RQ because we're going to have friction involved. And, of course, we're going to have friction involved. Now, what's going to try and happen is this is heavier than this. There's the same angle. So if there was no friction, then it would definitely move down this way. The friction wasn't there. It's going to move. P is going to move down, and Q is going to want to move up. That's the motion that is likely to happen, especially the angles are the same. Okay, the angles are the same. If this was a smooth plane and this was a smooth plane, which it is, this one is rough, this is smooth. Okay, if they were both smooth, then definitely the acceleration would be like this. This would go down, and this would go up. Okay. However, because it's a rough plane, we have to determine, are they going to move or not? So that means the thing that's, if it's, the thing that's resisting the motion would be the friction acting down the plane here. Okay. The frictional force, F, I'll call it FR. Okay. We don't know if it's going to be the same as F max yet or not. We'll have to find out. All right. So what we can do is we can consider the forces acting on P. So let's consider the forces acting on P first. Now the forces acting on P, we're going to resolve them in the direction of the motion that is trying to take place. All right, so I'm going to resolve the force, this weight, in this direction. Okay, the direction down the plane. Now I know this angle is 60. Okay, now this angle is going to be 30 because that's 90 here, right? So this is going to be 30. It's not going to be the same as the incline of the plane. The angle here would be 60. If I drew this line here, that would be 60. Okay, that would be 60. I could make that angle 60 if I wanted to. That's fine. But I'm just going to use this angle. I know that's 60. That's 30. I can do that, or I could call this 60 degrees as well. It doesn't really matter. Okay, let me just do that because that's I think what most people are used to. Okay, that means the angle there is 60 degrees. Okay, the angle between the plane and the weight, like the reaction force and the weight is 60 degrees. I'll just draw the reaction force here. Even though we don't need it, I'll just draw it anyway. Okay, so we know that this is the reaction at P, which we don't need because it's a smooth plane anyway, so there's no friction. And this is going to be the component of the weight, which is 0.2 G. Okay, this is going to be 60 degrees, so it's going into the angle cosine 60. And this will be 0.2 G times sine of 60. Okay, and on this side, we're going to have the components of the weight. Okay, down the slope and the component of the weight in this direction. Now this angle here is going to be 60 degrees as well. Okay, as is that. Okay, the angle between the weight and the the line of the reaction force, that's 60 degrees as well. So therefore this is going to be going away from the angle. it's going to be 0.1 times G times sine of 60. And this is 0.1 times G cosine of 60. Okay, so now let's consider the forces acting on P. Okay, you basically have these two forces. You have 0.2 G sine 60. Okay, you can say is equal to T. If it's in equilibrium, that's what's going to be happening. Okay, so that is equal to T. So T is equal to 0.2 G sine 60. So T is going to be equal to, that's going to be 2 times root 3 over 2. 2 times root 3 over 2, which is root 3 newtons. Okay, that would be the tension in the string. Okay. And for Q, we'll have T, if we consider Q, we'll have T minus 0.1 G sine 60 again, minus, or you can say, minus FR, or you can say T is going to be equal to that. Okay, so let's see what the frictional force is going to be. So you're going to have root 3 is equal to 0.1 times G is going to be 1, and sine 60 is going to be root 3 over 2, okay, minus FR. So you can say that the frictional force here is going to be root 3 minus root 3 over 2, which is going to be root 3 over 2. So that's the frictional force, okay, that's equal to. So for this to be in equilibrium, if it was in equilibrium, the frictional force has to be root 3 over 2, okay? So this is, we're considering the case if in equilibrium, this will be true. Okay, that means if the particles do not move, the frictional force has to be equal to root 3 over 2. Okay, now, can the frictional force become root 3 over 2? How do we know? Well, we have to think about what F max is. Now, if you remember, okay, just for those who are not sure, who have got lost now, maybe there's a few of you who didn't understand friction very well. If you have a rough surface and you have an object which is resting on the rough surface, okay, and, you know, there's no force being applied pushing any direction. It's just resting on the rough surface. It has its weight acting down. Okay, it has a reaction force acting up. You have its weight, you have its reaction force. If there's no force trying to push it, even though it's a rough surface, then the friction is going to equal 0. There will be no friction because nothing's trying to move it. However, if you have a force P, which is pulling it in this direction, okay, then there will be a frictional force acting in the opposite direction, which will try to stop it moving. Okay, now, that frictional force can vary from 0, if there's no force pulling it, to a maximum value that it can possibly take. What is that maximum value it can take? That's given by the formula mu times R. Mu stands for the coefficient of friction, which is like dependent upon the surfaces, the roughness of the surfaces that are in contact. The rougher the surface, the higher the value of mu. And R is the value of the contact force, the reaction force, which is perpendicular to the, the surfaces. So if F max is greater than the force that's pulling it, that means the frictional force will be able to match that force. It's not going to be more than that force if that force is less than F max. What it means is, wherever P is, the friction will match P. So if P is 5, the friction will be 5. If P is 10, the friction will be 10. Supposing 15 was the biggest value that the friction could be in this situation. If P is 15, the frictional force will also be 15. But if P is 16, the frictional force has reached its maximum value. It will only remain at 15, and this will be 16. It will start moving. It will not be in equilibrium anymore. Okay, so F max doesn't stand for like it's always going to be that value. It can reach that value. That's the highest value it can reach. Okay, that's what F max stands for. So in this situation here, for this to be in equilibrium, the frictional force here has to be root 3 over 2. Okay, because we've basically considered the forces acting on both sides. All right, for it to be balanced out, the frictional force will have to be root 3 over 2. Now, can the frictional force reach the value of root 3 over 2? That's what we have to decide now. Okay, that's what we have to decide now. So I'm going to work out what the value of F max is. Okay, so as I said, F max is equal to mu times R. Now we know mu is 0.7 as they told us in the question. Okay, the coefficient between the plane and the BC, between Q and the plane BC is 0.7. Okay, so we got to work out what R at Q is. So we got RQ is equal to basically 0.1 G times, and this is going to be cosine 60. And cosine 60 is a half. So the reaction force at Q is going to be 0.1 times 10 times 0.5, which gives you basically 0.5 newtons. So we can say F max is going to be 0.7 times 0.5, which is 0.35. Okay, and therefore we can say that the required friction is root 3 over 2, which is 0.8660. Okay, so we can say that the amount of friction needed is going to be so the friction needed, okay, is 0.860. F max is 0.35. So F max is less than the friction required. Therefore, the system will move. The system will move. Okay, will move. Particles are going to move because the maximum amount of friction that can be generated, okay, is going to be less than what's required. Okay, F max is 0.35, and we need a frictional force of 0.8660 to stop it from moving. Okay, so that is one way of answering this question. I'm going to show you another way as well. This is where we considered P and Q separate particles. Okay, and we worked out basically how much friction is required for this whole system to be in equilibrium. Right, there's also an alternative method. Okay, so the alternative method is if we consider like this as one whole system, in which case we can ignore the tension in the string. So that's an alternative method. As a connected particles, you can do that. So this is, for example, the weight here. This is the weight there. Okay, so this is 0.2 G times, as we said, if this is 60 degrees, that's going to be 0.2 G going away from the angles. Okay, sorry, going into the angle. Okay, 0.2 G. Okay, going into the angle, that way is going to be cosine, and this way is going to be sine. So this side is going to be sine, as we know. So this will be 0.2 G. 1 second. This is 0.2 G sine 60. Sine 60. And over here we'll have, remember this is also 60 degrees. Okay, according to the question before, this is also 60 degrees. Okay, so this angle is 60 as well. So you're going to have 0.1 G, and this will be 0.1 G times sine 60 as well. Okay, so we're also going to have on this side the frictional force. Okay, so this will be the frictional force here, acting down here. Okay, that's friction. Now, so if we consider this as one particle, it's like you can say that the force pulling on this side is 0.2 g sine 60. And the force pulling in the opposite direction is going to be 0.1 g sine 60 plus the frictional force. Okay, so for this to be in equilibrium, okay, for equilibrium, this has to be true. Okay, so we're considering the whole system. Okay, so the frictional force therefore has to be, that's going to be 0.2 g sine 60 minus 0.1 g sine 60, which is going to be basically 0.1 g sine 60, which is 1 times 10 times root 3 over 2. Okay, 0.1, sorry, times 10 times root 3 over 2, which is going to give you basically root 3 over 2. So the friction force has to be root 3 over 2, as we said, is 0.866 newtons. Okay, that's the frictional force that we need. And then the rest is the same. We can say, okay, let's work out what F max is. Okay, so for F max, we can say that we have the force acting, or we have the reaction force acting straight up. Okay, the reaction force acting this way. IQ, that's RQ. Okay, and that's equal to, you can say, 0.1 g going into the angle cosine 60. So we can say that F max is equal to mu times RQ, which is 0.7 times 0.1 g times cosine 60. So it's 0.7 times, that's going to be 1 times a half, 0.5, which is 0.35 newtons. So we can say that the friction required is equal to 0.8660, okay, and the maximum friction that can be generated is 0.35 newtons. So therefore we can say that, you know, the friction required is less than the maximum friction. Therefore, okay, the particles will move. The particles will move. I think this is a bit of an easy way of doing it than considering them separately, because they're connected with the same string. It's kind of like when you have the trailer and the car and they're moving, and you consider it as one whole thing, and you can ignore the tensions. You can do the similar kind of thing here, really. Okay, you see the force acting on P pulling down and Q pulling down that way, and you can kind of ignore the tensions in the string that way, and you know, you can get the answer in a more direct way. But when we're considering finding the frictional force, then we have to think about Q separately, finding what it is. Although we don't need the tension here, we just need the reaction force and the you know, the component of the weight to work out the value of the reaction force, so we can therefore work out what F max is. That's all. All right, so there's the answer to part A. Two different ways of doing it. And now I'm going to go on to part B. It says it's given instead that the plane BC is smooth. The particles are released from rest, and in the subsequent motion, the tension in the string is root 3 minus 1 newtons. Find the magnitude of the acceleration of P as it moves on the plane, and find the value of theta. Okay, so if the plane is smooth, if BC is smooth, there's no friction involved here. Now, they didn't tell us that the angle, last time they said this angle is 60. This time they have told us to find this angle, right? But they told us the tension in the string. So you got the tension in this string and the tension in this string, we know them both, right? So in this case, we have to really consider the particles separately because we know the tensions in the string. So let's go ahead and do that. Okay, let's go ahead and do that. Let's just consider the particles separately. So let's put some forces on here. So we have our weight and our weight. Okay, and they're smooth. There's no need to find any reaction forces now because both of them are smooth. This is 0.2 g, This is 0.1 G. Okay, and we can think about the forces acting in these directions now, resolving the force in this direction and resolving this force in that direction. Remember this angle here, or this, if you consider these lines here, this angle here is 60. This angle here is 60. Is theta. We don't know what it is. So we can say that this component is going to be 0.2 G times, going away from the angle, sine 60. And this is going to be 0.1 G times sine theta. Okay, so if we consider P, okay, it's accelerating. This will accelerate in this direction, and that will accelerate in that direction, because this is heavier than this side, so it's going to fall down this way. It's going to slide down this way, all right, because it's heavier. So we're going to have 0.2 G sine 60, because there's a resultant force now, which is equal to the mass times the acceleration. So 0.2 G times sine 60 minus the tension in the string is equal to the mass, which is 0.2 times A. Now with this, we can find the value of A, which is one of the things we have to find. Okay, so because we know that T is equal to, as I said, root 3 minus 1 newtons. So 0.2 times G is 2. Sine 60 is equal to root 3 over 2. So 2 times root 3 over 2. Okay, minus the tension in the string, which is, I'll put it in brackets so that I don't mess up with the minus signs, root 3 minus 1 equals 0.2A. So the 2's cancel out. You're left with root 3 minus root 3, which is 0, and plus 1. So it's going to be 1 divided by 0.2 equals A. So 1 divided by 0.2 is 1 divided by 1/5, which is 5. So it's 5 meters per second squared. That's the acceleration of the particles as they, of P as it moves down the plane. Okay, and of course it's the same as the acceleration of Q, because they are connected by a light inextensible string. But that's the acceleration of particle P. And then we've got to find the value of theta. So I know the tension in the string. Okay, I can resolve the forces for Q now. I can say that Q is going up, so T minus 0.1 G times sine of theta is equal to the mass of Q, which is 0.1 times its acceleration. So now I know that tension is equal to root 3 minus 1. I know the acceleration is equal to 5. So I have everything I need to find the angle. So you're going to have root 3 minus 1 minus sine theta, because this is going to be 0.1 times 10, which is 1, is equal to 0.1 times 5. So we can say root 3 minus 1, and that's going to be minus 0.5 is equal to sine theta. So sine theta is equal to root 3 minus 1.5. So theta is equal to the inverse sine of root 3 minus 1.5. And we can find out what that is. And that should give you the angle. So we have shift sine, degree mode, yes, root 3 minus, make sure you make a space after the root so the root stops there, minus 1.5. And that gives us 13.417. So theta equals 13.417 degrees. We should give our answer, it didn't say anything else, so to 1 decimal place for angles in degrees. So you have 13.4 degrees. And there is the answer. Okay, those are the answers to this question. The acceleration of P is 5 meters per second squared, and the angle theta is 13.4 degrees. We use the fact here that the acceleration of both particles are the same, okay, by putting A as 5 here, because they're connected by a light inextensible string. Okay, so there's the answer to part B of this question, and that completes this question, all right, from the June 23 paper. Other questions from this particular paper can be found in the playlist that will appear in this section over here. Other questions from the topic of, I guess this is to do with statics and also a bit of dynamics. Okay, forces and friction. I'll put a few different playlists here this relates to. Mechanics questions are always intertwined with different topics together in a lot of cases, especially like this type of thing. So thank you for watching and see you soon.